So welcome everyone to the Winds and Currents webinar. We're fortunate today to have Brian Arbic, who's going to talk about, he says, 3 topics: near surface oceanic kinetic energy distributions from drifter observations and numerical models, and I think a couple other things as well.
Yeah, should I go ahead?
So go ahead, Brian. Thanks for being here.
Yeah, thanks. So you can see my screen and hear me and everything?
Yes.
Okay, great. Yeah, so I'm going to talk about a comparison of HICOM, which is the U.S. Navy operational model, and the famous MIT GCM LC 4320 simulations from JPL and NASA. I'm going to compare those to drifters. That is a paper that we just got minor revisions on last week, so it should be published in a month or two. And then I have 2 other Odyssey relevant topics that I'll talk about briefly. So the main topic is the drifter comparisons. This work, I consider Shen Elipo to be basically a co-lead author. He's been working with drifters for years. By the way, he was Sarah's PhD student. I also want to highlight that there are many co-authors, and 3 of them were undergraduate computer science majors. As a professor, I like to involve some undergraduates in research. Okay, so we're going to compare the velocities at the sea surface, or 0 meter depth, and at 15 meters in global high resolution HICOM and MIT GCM versus undrogued drifters, which are meant to represent flows at the surface, and drogue drifters, which are representing flows at about 15 meters. And we're comparing these in different frequency bands, ranging from low frequency or subtidal all the way up to semi-diurnal high frequencies. We do compute a vertical structure proxy ratio, the ratio of kinetic energy at the surface divided by the sum of the kinetic energies at 0 and 15 meters. So if there was no vertical structure, then that value would be 0.5. If it's greater than 0.5, that means you have a top-heavy velocity field greater at the surface. And if it's less than 0.5, that means velocity decreases with depth. We are following work by Yu et al., who compared the MIT GCM to drifters. They did not emphasize the 0 to 15 meter contrast at all. They just said, you know, they're getting about the same results in terms of the way the maps look, but they didn't look at this vertical structure. They did show that the near inertial flows in MIT GCM, the particular LC 4320, was too weak relative to observations, and the semi-diurnal kinetic energy was too strong. And that was a major motivation for our study, because I had a feeling that HICOM would lie closer to the drifter observations in those bands. But as you'll see, we have more results than just that. So hopefully the relevance to Odyssey will be clear. Drifters and high resolution models can both be used to examine spatial geography and in different bands, so frequency content of the near surface KE. And also, I've asked a few of you about this, since people seem to agree that some knowledge of vertical structure will be helpful for Odyssey, because if you're measuring velocities at the surface, you want to know what that implies for velocities as you go down into the ocean. So again, the main topic is this drifter basically in press drifter paper, but I should have time to present on briefly on 2 other Odyssey relevant topics. We've simulated a computation of the spectral kinetic energy cascade from Odyssey. Alex Winatier helped me, sorry if I mispronounced the name, helped me prepare that, and I did that calculation this weekend, kind of a quick preliminary result. And then following Patrice's talk on air-sea interactions, I just want to show a couple slides at a paper we published on high-frequency precipitation variance computed from coupled high-res atmosphere-ocean models, as well as observations. So that's a diagnostic model data comparison relevant to air-sea interaction. Okay, so the observations and models used, we use observations from the Global Drifter Program, undrogued at the surface and drogued at 15 meters. We use 2 different simulations. Both of them have tides embedded in them. Global 125th degree HICOM. The assimilative version of that is used for Navy operations. We're showing non-assimilative simulations here. There's 41 hybrid layers in the vertical, 7 Z levels in the uppermost 30 meters. So we have some resolution of vertical structure. We do include a parameterized topographic internal wave drag to roughly account for unresolved breaking internal waves. We've been arguing this for a long time, that if you make the waves, but you don't actually break them, of course, global models don't break them. So we argue that you need a knob to stand in for that missing breaking. And that matters for the tides. We have 3 hourly atmospheric forcing in this particular simulation. And in the interest of honesty, because I'll talk about flaws of both models, HICOM has a numerical instability in the North Pacific. I'll show it to you, and it mostly affects the semidiurnal band. So the MIT GCM is global 148th degree with 90 Z levels, 13 Z levels in the uppermost 30 meters, doesn't have wave drag. That will really affect the tides. It has a 6 hourly atmospheric forcing, which is very important for the near inertial oscillations. But later in the talk, we'll show preliminary results from a coupled atmosphere ocean simulation. And the thing about when you couple is that you have very frequent atmospheric updates, and that makes a big difference to the near inertial oscillations. So we'll use frequency spectra to separate kinetic energy into different bands, and we'll compare drogue drifter results to the model results at 15 meters, undrogue drifter results to the model results at 0 meters. And again, we have this proxy ratio to tell us something about vertical structure, 0 to the sum of 0 divided by the sum of 0 plus 15 in the models, and undrogue divided by the sum of undrogue plus drogued in the drifters. The drifters are quite noisy. We are, of course, aware of that. You can see that in the observations, but nonetheless, hopefully I'll convince you that we do see some agreement between the models and the drifters in these ratios in some frequency bands, not all of them. Well, zonal averages, kind of all of them, but point by point, it depends on the band. So the band definitions, we follow what was done by you et al., which was a motivating paper for us. So low frequency is less than 0.5 cycles per day. Near inertial is 0.9 to 1.1 F. Diurnal is 0.9 to 1.1 cycle per day, which means that the near inertial and diurnal bands overlap near 30-degree latitude. And then semi-diurnal, their definition is 1.9 to 2.1 cycles per day. So we just compute frequency spectrum and then integrate in those bands. So the zonally averaged rotary spectra, so we have frequency on the x-axis and latitude on the y-axis. From the undrogued and drogued drifters is at the top, HICOM 0 and 15 meters in the middle, MIT GCM at the bottom. This feature here is the near inertial band, very strong. The 0 is, of course, the low frequency. That's the strongest flows of all. You do see peaks at the diurnal and semi-diurnal frequencies and their harmonics. And you can see that in the models, those peaks tend to stand out above the background more so than in the drifter data. This is a log scale. Or another way to say this is that the tidal peaks tend to be wider in the drifters. They blend into the background and don't stand out above the background as much as they do in data. This is an important fact for the semi-diurnal band especially. There are papers already in the literature about this, several of them, which we cite in our paper. But basically, if you imagine that the world only had semi-diurnal tidal peaks, but that they changed in space, then a Lagrangian sampling of that will actually tend to widen the peak. And so Lagrangian spectra are by nature, they tend to be wider than Eulerian spectra, at least in the tidal band. That fact will matter later. Okay, so the maps of the low frequency kinetic energy are here. You have MIT GCM 0 and 15 meters here, HICOM 0 and 15 meters here, undrogued and drogued drifters here. I'll talk about the bottom ones in a second. You see the well-known western boundary currents, Gulf Stream, Kuroshio, ACC, etc. You also see a lot of energy along the equator. So one thing that's worth mentioning right away is that in Yu et al., what Shen Elipo did for that paper was he took 60-day segments of the drifters and then computed the spectra in various bands from each segment, and he assigned the energy values to the mean position of that 60-day drifter segment. And because of divergence at the equator, he ended up not getting much data on equatorial points. So now he has a new way of doing it, which you should ask him or read the section in our paper that he wrote, where basically he takes points on the equator or anywhere else and just looks at all the data passing through it. And so that is a way for him to assign energies to equatorial points so that you don't have gaps on the equator. He actually gets a better spatial correlation between the models and the drifters when he does it that way, at the same time that there's less gaps. So he's pretty happy with that new way of doing things. So the spatial correlations are given here. I won't go through all of them, but these numbers are the correlations between the two model runs. The blue ones here are the correlations between HICOM and the drifters, and the gold ones are the correlations between MIT GCM and the drifters. And in most, if not all bands, the HICOM correlations are higher than MIT GCM, but sometimes by just a tiny bit. So moving to the vertical structure plots, which is shown on the bottom, the correlations of HICOM to the drifters or MIT GCM is actually fairly high. They're shown here, 0.48 and 0.41, fairly high considering that there's so many degrees of freedom. Look at all the grid points that you have there. At least I'm not a master of stats, but Shen says it's fairly high given that. And so you can by eye, you can see these patterns in red here that you can also kind of see in the drifters, and see these patterns in blue along the equator. So on a point-by-point basis, the drifters are noisy, but I hope this shows you with the spatial correlations and the visual similarities that there are some similarities in this proxy ratio between models and data. And so when we look at the zonally average low frequency kinetic energy of kinetic energy as a function of latitude, let's see, the drifters are in gray, HICOM is in blue, MIT GCM is in gold, 0 meter and undrobed is here, 15 meter and drobed is here. And you can see some levels of disagreement, but there's certainly some general similarities. And the one point I want to make here is the biggest source of disagreement is on the equator. And this is a point I want to emphasize a little bit here, that we're used to comparing eddying models to altimetry. And when we're looking at kinetic energy in particular, you have to make the geostrophic assumption if you're using altimetry, so you can't do much right on the equator. Here we have a data set, drifters, where you can look at velocities on the equator, and Odyssey will be the same. And so I think the equator is really interesting. It also happens to be the place where the absolute discrepancy between models and data is largest. So when we go to the other bands, pay attention to the y-axis, you'll see that it drops by quite a bit. The maximum value is quite a bit lower. So what I'm saying is that the low frequency flows are the strongest flows, and the low frequency flows on the equator are the strongest of all, at least in a zonal average. So you're not seeing this signal in altimetry, right on the equator at least. And there's a big discrepancy between models and data. So this is pretty interesting. I'll get back to that later. The vertical structure proxy ratio we talk about, it does lie above 0.5 for most latitudes. And HICOM in blue is within error bars of the drifters in gray. The error bars are big. And then MIT GCM is also in the error bars over most latitudes, except for some reason not at the very high latitudes. So it's worth pointing out that the low frequency band does include Ekman flows, which, as we all know, have a lot of vertical structures. So part of what we're seeing here is probably Ekman flows, although we didn't diagnose that any further than just what I just said. Okay, so moving to the near inertial band, which is the next largest source of kinetic energy at the surface, you can see that you have significant near inertial flows at high latitudes in all three products, fairly high spatial correlation coefficients, again, considering the number of degrees of freedom. You can see already that MIT-GCM, since this is a log plot, MIT-GCM is noticeably too weak. This is a band where the point-by-point correlations in the vertical structure are basically not significant. You know, they're basically zero. So when you look at the zonal averages, the highlights are that MIT-GCM is too weak basically everywhere, and HICOM lies closer, although in the high latitude, in the high northern latitudes, although HICOM lies closer, it's still far away from the drifters, and that is another point I'll return to later. When you look at the vertical structure proxy ratio, again, there's always big error bars on these, but it is slightly greater than 0.5, so there is some top-heavy, surface intensified vertical structure in the near inertial band. Of course, that's well known. Now, the diurnal bands are in some ways the most complicated, and they're so complicated and interesting that I'm actually not going to show them in detail here because it would take just too long. But they're complicated and interesting. And one of the things that's interesting that we found in this paper, you et al. Didn't show this, but as a tide guy, I just naturally assumed that the diurnal band was dominated by tides. But if you actually do a tidal harmonic analysis and you look at the maps and zonal averages of the kinetic energy inferred from a tidal analysis, and you compare that to what you might call the full diurnal kinetic energy, which is computed from frequency spectra, you can see that the clear implication is that the diurnal band isn't just tides, because the true tides as inferred from a harmonic analysis are often substantially weaker than what you get from the band integral. So we know that the diurnal band includes not just diurnal tides, but it includes an overlap with the near inertial flows near 30 degrees latitude, just the way we've defined things. But even outside that, the tides are often weaker than what you see in the full diurnal band, as I'm calling it. So our best guess at this point is that we're seeing diurnal cycling of Ekman near inertial and submesoscale dynamics. This first paper that we're doing here is quite broad. We're looking at lots of frequency bands and vertical structure. We don't explain everything that we're seeing, and we're saving some things for later work, but there's a lot to be done in the diurnal band. But moving on to the semi-diurnal band, you can see the well-known internal tide generation hotspots at Hawaii and French Polynesian Islands and other places. And they're right here in this circle. I'm trying to get my cursor there, I'm having a hard time. There it is. This circle here in HICOM, that is a numerical instability. So that is not physical. That's a problem that we have in HICOM. The vertical structure in the semi-diurnal band is fairly limited. It's pretty close to this 0.5 value, but there are some hints if you look at the Gulf of Mexico and the Caribbean and these places in the Southern Ocean, where you see some reds that you also kind of see in the drifter ratios. And again, the correlations, though low, are actually statistically significant because there's lots of degrees of freedom. When you look at the zonal averages, there's a lot to be said about the tides. So the fact that MIT-GCM in gold lies far above the drifters, that was noticed by you et al. In 2019. And one of the reasons we wanted to also compare HICOM. So HICOM in blue is closer to the drifters, although still higher in most latitudes. But here, that is also partially due to that unfortunate numerical instability that HICOM has. So HICOM is closer. Now, we have done quite a lot of investigation of the MIT-GCM forcing. of the tides, and there are mistakes in it. And we're documenting that in a paper that is in advanced preparation. We hope to submit in the next few months. But we've taken a barotropic tide model and done experiments with the incorrect forcing. And we think that the incorrect forcing can only explain about 17% of the discrepancy, whereas the MIT kinetic energies are often 4 times larger than the observations. So that tidal forcing mistake should be documented, but we don't think that's the main reason for the discrepancy. We think more important is the absence of a parameterized topographic wave drag in MIT GCM. We've, again, written a lot about that in our own papers. And so all that will be documented in this paper here, which is focusing on the internal tide SSH. The differences in kinetic energy are actually larger than you see in internal tide SSH, and that's probably because drag acts on flows, not on SSH. The vertical structure, by the way, within error bars is basically shows very little vertical structure. One other thing I'll mention is that HICOM is an operational model. We've tuned it for years to be close to the observation. So we were surprised about the size of this discrepancy. And so we were thinking that maybe part of the discrepancy between MIT GCM and the drifters might have to do with that Lagrangian width thing I talked about earlier. So if instead of slavishly following U's definition, we widen the definition of the semidiurnal band, that's what we do here, you can see that MIT GCM, no matter what, is always well above the drifters, gold above gray. But at some point, the drifter energy is lifted up. Again, it is wider, so that makes sense, so that it actually is pretty close to the HICOM values over a lot of latitudes. So, you know, to really be sure of that, we should actually seed HICOM with drifters, and we haven't had time to do that yet. But this is at least suggestive that the HICOM kinetic energy might lie closer to the drifters than you'd expect from this first plot here. So the conclusions from this in minor revision paper is that drifters are a great data set to discriminate differences between models. HICOM lies closer to the drifters in near inertial and tidal bands than MIT does for different reasons. Atmospheric forcing updates for near inertial band and wave drag for tides. The diurnal band is super interesting, and we have a proposal by Shen Elipo and Dan Witt to study that with me and Dimitrion as unpaid older folks providing model results. But another really interesting place is the equator, that the models are way off on the equator, and that happens to be the largest signal in the drifters, at least in the zonal averages. And then these words here are saying we have some skill in the vertical structure that we think is important for Odyssey. Some other ongoing and future work aside from the proposal on the diurnal band, and we'd like to look at the equator more, is to look at a coupled ocean atmosphere simulation of MIT GCM with GEOS, and the rest of my talk will be about that. But the Navy has its own version of coupled ocean atmosphere simulation, some of which are operational. And so what I want to do now, this is not in the paper, but it'll be in future papers, is preliminary drifter comparisons with the coupled ocean atmosphere model. So now the blue denotes the uncoupled MIT GCM that we've been looking at before, and the gold represents the coupled. And so I personally think it's really interesting that when you have the much more frequent coupling, you crank the equatorial energy up by quite a bit, and it starts to get closer to what you're seeing in the drifters. And again, this is the largest signal in the, at least in the zonal averages that you see in the drifters, is right here on the equator. So I personally think that's pretty interesting, that having high frequent updates of the atmospheric coupling makes such a big difference. And so we will surely keep looking at that. The other major result we get with the coupling is a big improvement in the near inertial band. So MIT GCM, when it's not coupled, is here in the blue. And when it's coupled, it comes up a lot closer to the observations. And so this means that you can use the coupled simulation to reliably estimate near inertial oscillation aliasing errors when you're thinking about Odyssey. And Jinbo Wang is writing a paper about that. Okay, so now having said a little bit about the coupled model, which I'm sure everyone here has heard about, it's heading towards, I think, a 1/48th degree ocean and I forget exactly, 1/32nd degree atmosphere, maybe Dimitri or Patrice would know. I want to show very quickly two other Odyssey relevant results from those simulations. So first of all, I suggested to a few of you that we should simulate the computation of spectral kinetic energy cascades in Odyssey data. So totally shifting away from the drifter comparison, but still Odyssey relevant. So Alexander Winnetier very kindly went in to those model results at JPL, and he took 1,731 hourly snapshots of the surface flow in the Kuroshio region over this 70-ish day period. And a sample snapshot of the kinetic energy in that Kuroshio region is shown here. There's no noise in this. It's just the native model, as I call it. Then what Alexander did is he gave me 90 snapshots of Odyssey samples of that region. So with and without noise. So that's at the sampling periods, expected sampling periods. That's why there's less snapshots. And he also put noise in it. And I have to say, from looking at the noise, it's intimidating. Someone like me who has done a lot of stuff with spectra, it's very high amplitude and very relatively small scale. So I didn't think that just shoving that through my spectral kinetic energy cascade machinery would work very well. But I think it actually did. So when you look at the time average spectral kinetic energy flux from the native model, that's the black curve. From the Odyssey samples, that's the cyan curve, not very different. And to my pleasant surprise, even the Odyssey samples with noise is not that different. There you see it's different, but it's not that different as a first cut, something that you bang out in the weekend. Not too bad. Yeah, this is a spectral K cascade that uses the full velocity fields, not just the geostrophic velocity fields, for those who know about these technical things. When you're using the geostrophic stream function at the low wave number end, it has to go to 0, but it doesn't have to go to 0 when you're using the full velocity field, not just the geostrophic part. When you're using the full velocity field, you're going to have internal waves and perhaps submesoscales, whatever you resolve in this simulation, which happens to be 1/24th degree. So you are seeing a forward cascade, these positive values at high wave numbers, and then here's an inverse cascade at somewhat lower wave numbers. So I think that more could be done with the included noise computations. There are things out there called noise suppressing differentiators, which are well known in the numerical literature, and I wrote about applying them to, I was thinking about altimeter data in this JGR paper, but so probably a better job could be done than just shoving it through a usual spectral differentiator, which is probably going to really amplify the small scales. And it's maybe worth mentioning that the variability in the spectral flux from one snapshot to another is massive. And it's really large in the with noise computation. So you really have to do a time average to get agreements this good. So I think more could be done with that noise, but I just wanted to do something quickly, and we're already talking to Lionel and others about improving this, and I think it's looking like an interesting start. Okay, so sorry to shift gears again, but my last 3 slides, I want to talk about another application of the coupled MIT GCM geo simulation. And it may seem not exactly Odyssey relevant, but it does have to do with air-sea interactions. So Patrice Klein last week gave a super discussion of air-sea interactions, which is a goal of SWAT and Odyssey. And we have a paper that was published earlier this year in Climate Dynamics, where we compared the high frequency precipitation variance in this simulation and other high-res coupled atmosphere ocean simulations with observations. So precipitation is certainly an important climatic and weather variable, and it's part of air-sea interactions. And so the intuition that I have as someone who's never written about precipitation before, but lives on planet Earth, is that precipitation often takes place in brief but intense events. And going along with that, a paper by Covey, Trenberth, and others, they demonstrated that most of the precipitation variance in the CMORPH satellite-based product lies in what they call irregular subdaily periods. So periods that are not, like 3 hours, 6 hours, 12 hours, which divide right into 24 hours, but actually are, not those integers. But anyway, fast periods that are not divisors of 24 hours, that's where most of the variance is. Actually, as they say, by far, most of the variance lies in that. So most of the variance is in fast periods. And as you would expect, and as they show, low resolution climate models do not at all capture this high frequency nature precipitation, not even close. So in our paper, we demonstrate that high resolution coupled ocean atmosphere models capture much more of this irregular subdaily variance. So the US Navy Earth System Prediction Capability Model lies close to the CMORPH observations. That's, not a fair comparison in a way, because that's a forecast model, and so they're assimilating those observations. But anyway, good news that it lies close to it. The MIT GCM GEOS atmosphere model overshoots the observations. So just kind of a humorous observation. Dmitry Manomenelis is one of my best friends in the field, but we have written a lot of papers where we show that the tides in his simulations are too large, and now we're showing that his precip is also too large. Anyway, so we have good fun writing these papers. The Covey et al. Variance analysis can't be performed on many simulations because they do not save at subdaily intervals. So even simulations where people resolve the eddies, and they do these beautiful simulations where the atmosphere is coupled to an eddying ocean, they still save like daily averages, and you can't look at this subdaily precipitation, which is where most of the variance lies. So just two more slides looking at frequency spectra that's separate from that variance analysis I was just discussing. So here you can just see a few things here. So here we're averaging some rain gauges in the Atlantic coast region of the US. And that's this orange curve. You can see that CMORPH lies below that at the very high frequencies. The Navy model is this dashed line right on top of CMORPH. There's some other products that are lower here, but then the MIT GCM GEOS simulations, at least the ones that we looked at, actually lie above that, as I was mentioning. Now, those were early versions of those simulations. The more current ones might be a little different. Here are some CESM model runs and some GFDL model runs. And it's a little hard to see all these curves. Sorry about that. But the CMORPH is in cyan. You can't do the CESM past this 1 day mark here, as I mentioned. The high CESM high has an eddying ocean, and that is, I think that's this curve here. Whoops. This curve here on top of the cyan. And one of the CESM low resolution models is this dashed curve here. So we're looking at variance here between 2 and 100 days. So not really high frequency, but relatively high frequency compared to climate. And the point is that you can see more precipitation variance in the CESM runs when you have an eddying ocean. Now in the GFDL suite that Stephen Griffiths and collaborators ran, you don't see as much of a difference. If you integrate this, you can see that when you have an eddying ocean, you do have a little bit more precipitation variance, but it's not as big an effect as you see in the CESM runs. And we think the reason for that is that the CESM runs had a 1/4 degree atmosphere and the GFDL runs had a 1/2 degree atmosphere. So it seems that the eddying ocean does make a difference to the precip variance, especially when you have a higher resolution atmosphere to accept those high resolution fluxes from the ocean. So it's outlined in the paper. It's actually in some tables, perhaps a little more clearly than you can see in these spectra. So the point of that paper is that A decrease in atmosphere ocean model grid spacing leads to higher precip variance at high frequencies. The ocean model grid spacing does matter, but especially when the atmospheric model has relatively fine grid spacing also. And the new MIT GCM geosimulations have too much high frequency precipitation variance, but I haven't looked at the very latest simulations of this, which are even higher resolution. So I don't know which direction things will go there. And one last thing I'll mention is that Charles Light was an undergrad. This is something I've really done a lot of the last year as a professor. 5 papers from my group are led by undergrads. And it's a lot of work to have undergrad-led papers, but it's certainly a good experience for them. Okay, so I've said enough. I'll stop there.
And thanks, Brian. That was great. There has been a very active discussion in the chat, so maybe.
Yeah, sorry about that. I saw that. I just didn't want to.
Well, that gives us questions to get started.
Yeah.
So first question is, why is the background in drifters higher than in the models? How is that expected?
Yeah, that's a great question. And I can't tell if Shen is here. I think he said he might not be able to make it. He's the better person to answer it. But some of my extra slides, you can really see that here. So here's the drifters here, and then the models are below that. It's essentially noise. The answer is noise. And it has to do with the tracking, something I didn't mention today, but the older drifter data was tracked by something, I think it's called Argos, and now it's GPS. And the GPS track drifters have a much lower noise floor. It instead of like this, it's like if you divide the drifters up into GPS and Argos, then it's a much steeper spectrum in the Argos, and it actually agrees pretty well when you compare only the Argos one. It agrees pretty well with the MIT model, the higher resolution MIT model.
So, and then Clemal Ubelman went on to ask, are Stokes drift and wind slippage estimates removed from the undrugged drifters before comparing to the first layer of the model?
So that's definitely a question for Shen. I think the answer is no, but Shen is the one who prepared the data and did all the data analysis, Shen Elapo. So I don't want to say too much more. I think the answer is no, but Shen would know for sure.
Yeah, it looks like he's not here, so we'll have to email him to ask. So I urge people to raise your hands or put additional questions in the chat, but I'll just keep going through these. Megan Cronin noted that diurnal kinetic energy could also be due to diurnal jets trapping wind momentum within the shallow warm layer.
Yes, thank you, Megan. I'm going to click on that and mark that reference because I'm making the final revisions to the paper basically today. I mean, it's minor revisions, so probably accepted. So I'll stick that reference in there. Yes, good. I don't know much about diurnal jets. As I said, Shen and Dan Witt have a proposal in to look at them. I've heard the word diurnal jets. I didn't realize diurnal jets are different from those citations I had, the Price et al. And those others. So I'll take a look at that.
So is the strong currents in the afternoon?
I don't know.
With actually. The diurnal cycle, that would be indicative of this momentum trapping.
Yeah, I don't know. I mean, analyzing these huge models and the drifters and comparing them across many bands, we kind of made a decision that the first paper would be really descriptive. It's just like, here's all the stuff we see. And then we'll try to run follow-on papers, really look at things in more detail. So the kind of thing you're talking about, like, is it in the afternoon? We'll do that in follow-on papers.
Okay.
Yeah, but I'll look at the papers so that at least we have a more complete citation in our paper. Thanks.
And Fabrice has just added another one.
Oh, Fabrice just said? Okay. Okay, thanks, Fabrice. Oh, and Tom says they're not that different. So maybe Tom, are you, this is what, I'm not at all an expert on diurnal jets. I thought that the stuff I showed, diurnal cycling of Ekman and near inertial and other things, I thought that was related to diurnal jets. Is that what you're saying, Tom, that I was maybe right about that?
Yeah, I mean, it's a wind-driven signal that's diurnal because of the day-night cycle of sun stratifying the upper ocean. It's just what was described in Price, Weller, Pinkel.
Okay. Thanks, everyone. I'll still cite those more recent papers too, that what the heck, add some more recent ones. Melanie's question, able to separate the wind-driven and tidal contributions today. Oh, okay, great. Okay, so here's another one. All right, I'll mark those too. Okay, thanks for that, Melanie. If nothing else,
Yeah.
citing these more recent papers will help us if we actually get funded to look at this. So,
And Mo Mayhell has his hand up.
Yeah, nice. I have a question about, first I have a comment about the jets. There's also nocturnal jets in the atmospheric boundary layer, which leads to the other question about the SC interaction and the precipitation papers. So if I understand that correct, even if both model components would represent the total amount of precipitation or the total amount of variance in both systems correctly in lower resolutions, if you want to couple them, we have no other possibility than just going to very high resolutions to get to like actually feed off this variance, which is in the precipitation as you showed. But I guess if you're in the ocean, it's also in the winds, because precipitation comes often in fronts and there are wind patterns associated with it. So that means we have to go to couplings that are on these you had this nice term of like on these unperiodic sub-daily scales. That's what I get from that.
So if I get what you're saying, are you just basically saying that when you go to these high risk coupled models, you have to think a little harder about the bulk drag coefficients and how you do the coupling?
No, I'm just thinking about that. Even like, so what parameterizations do, they represent subgrid scale processes such that we can run the models on lower resolutions and lower time steps, which is fine to like to constrain their budgets and like take account for the variance that is not resolved. But if you want to couple them, since we have two different systems that now communicate with each other, you have to get rid of this, these approximations, these parameterizations, and you have to go to high resolutions to actually make the precipitation correct, make your filaments correct in the upper ocean, make your fronts correct in the atmosphere, because otherwise you will never get the fluxes at the right frequency.
Yeah, so this is another case where, we wrote a descriptive paper on, anyone can compute a frequency spectrum, even someone like me who doesn't know anything about atmospheric parameterization. So, but it's kind of interesting as someone who runs these big models, the modeling centers are all talking about climate and weather models coming together. And weather models are going to be high frequency and looking at events on hourly timescales. So I'm rambling a bit, but doesn't it seem like that this is something we really need to think about? Because if the climate models and the weather models are moving together, if they're supposed to be the same cores as everyone is saying, and the weather models have to work on hourly timescales, right? Am I making any sense here?
Yes, I'm not really asking a question either, but it was more a comment.
Yeah.
Thanks, though.
Yeah, thank you.
And,
Well, one thing I'll also say I've heard from some of my atmospheric modeling friends is that it apparently makes a big difference whether the atmosphere is hydrostatic or non-hydrostatic, what it does with precipitation, which even I can understand that, because obviously deep convection is a non-hydrostatic process. So I think that's another thing is whether these models are non-hydrostatic probably makes a big difference. I don't know if you'd agree.
We got a couple more hands up. Mara Freilich.
Yeah, I guess just to follow up on that was to ask if you have a sense if improving the frequency, so shortening the time step of a model, matters more or equally to changing the spatial resolution. So you showed that the eddying model has more accurate precipitation variance. Is that because the eddying model has a shorter time step, or is it because of feedbacks between the eddies and the atmosphere that improve precipitation variance?
Again, I hate to sound like a dope, but our paper was just very descriptive. So I
Okay.
don't know the exact answer, but I mean,
I guess maybe
Well,
as a modeler.
yeah, I mean, as
but-
Patrice beautifully discussed last week in more detail than I could hear. I mean, we all know from Dudley's work, and Patrice showed it, that we're starting to believe that eddies influence the atmosphere. And so one would think that if you have high resolution eddies, and again, like, I think it's really interesting, the difference between the NCAR, CESM, and GFDL model results, that I don't know if you could see it very well from the spectra, but when you look at integrals over the spectrum at one of our tables, you can really see the difference, that if you have GFDL half-degree atmosphere and you go from a 1 degree ocean to a quarter-degree ocean to a 10th degree ocean, the precip variance increases by like 10%. But in the CESM runs, where you have a quarter-degree atmosphere instead of a half-degree atmosphere, it doubles. So, you know, just looking at those facts, it seems like if you have a higher resolution atmosphere, you can accept those high resolution fluxes better without having to smooth them out. And so that's probably why the NCAR model sees a bigger effect, but I'm kind of waving my hands here. That's my guess. Justin Small was on the paper and he didn't disagree with that interpretation. He's one of the CESM people. I don't know if that's a very satisfactory answer. That's just my guess.
Yeah, thank you.
I see Frank's on the maybe Frank has thought more about this kind of thing than me.
Yeah, I can't really speak to the atmospheric stuff very deeply, but you know, as you mentioned, these are hydrostatic atmospheric models with some parameterization of deep convection, and the amount of the precipitation that's being taken up by parameterized convection by what's left in the explicit lifting, the large scale motions could be quite different between GFDL and the CESM models, because we use different representations of deep convection. So I think it's perhaps not just the factor 2 difference in resolution, but the combination of the different parameterization suites we're using.
Yeah, fair enough. Thanks, Frank.
And Fabrice Sardouin has his hand up.
Hi, Brian. It's a great talk. And it was really nice that you have this data set now with values on the equator. I'm still trying to think that there's not a bias in the method for estimating that, but let's say that it's good. Data is good. It's what's your guess for this huge difference in the kinetic energy at the equator? Are we just missing the stratification? I mean, I guess your comparison of surface with undrogued and drogued seems that you're getting a similar ballpark, but that's also true at the equator. Is it how do you explain that if you can? I don't know.
Well, yeah, there's a lot in that question. Yeah, the bias is worth pointing out. I mean, you really have to read. Anyone who's interested, I can send you the paper now, but it'll be published soon. You have to read the section where Shen Elipo describes his drifter analysis carefully, because he did that part, not me. But in the end, you are comparing, Lagrangian drifters to Eulerian models, so the possibility of a bias is there. When he completely changed methods, as I described, we still kind of see that discrepancy at the equator, and the fact that the undrogued and drogued drifters give similar results, to me at least, suggests that well, it's good news that they give fairly similar results anyway. It would be bad news if they were really different. As far as the equatorial dynamics, this is yet another thing where, I'm a tide guy. So what happened is you had all wrote that paper in You know, the near inertial waves are too weak and the tides are too strong, and MIT GCM. So I think you even might remember me saying, I'm sure HICOM will be better.
Yeah.
Then we just went in all these other bands that I know less about. And, you know, so I'm not an equatorial dynamicist. I saw Tony Lee was, oh, here, he's still on the call. He knows a lot more about equatorial dynamics, and he was telling me something about in our plots, I could pull it up. One of the places where the coupling brought the energy up, he's like, oh, that's probably this ITCZ effect in the northeastern Pacific. I don't know if Tony wants to come to my rescue here, but he knows more about that stuff than me. Do you want to say
Okay,
Tony?
thanks.
Hi, Brian. Let me try to remember what I said to you. I think I was referring to the high frequency precipitation effect that may not have been captured by the models.
You were referring to this thing right here.
Yeah,
The fact that in the near equatorial but north of it,
right.
Pacific, that the coupling in the MIT GCM made the biggest difference right here.
Right. Right. So in the MIT GCM, where you have 4 hourly forcing,
Yeah,
it
6
does
hours.
not represent the precipitation effect on stratification correctly. Whereas you do better in a couple. Maybe that's one of the reasons. And since I got the mic, I also want to ask the right question. If you sample the model like drifters, that will allow you to address the potential impact of the Lagrangian versus Eulerian.
Yeah, for sure we should do that. We haven't done that for the HICOM. Maybe, oh, I see Dimitri's on the call. Dimitri can say something about the MIT ones. I think that has been done by Ryan Abernathy, maybe Aurelian Pont too, I'm not sure. Yeah, Dimitri.
So one more area that may be causing the difference, and I think it was also pointed out by Tony, is the simulation, at least the MIT GCM and the coupled MIT GCM is 1 year, 14 months, while the drifter data, they can't do it with just 1 year, so they're including, you know, multi-year observations which have answer variability and other stuff that's happening that may leak into this analysis. And I think that was also your point, Tony, or oh no, maybe it was Jorge who did that when Brian gave his talk at JPL.
Yeah, thanks for bringing that up, Dimitri. We mention all this in the paper, but sometimes you forget to say it in the talk that the drifter data isn't dense enough to do year by year. So and the models are too expensive to run much longer than a year. So there's a lot of not apples to oranges. I'm sorry, not apples to apples comparisons in this paper. Again, typical of kind of a first look. And someone asked in the chat, you know, couldn't we just simulate the drifters in the models? Yes, we could. It's been done for MIT GCM, but that was kind of after we started our project, and we didn't do it for HICOM. And you know, these model outputs are so huge that all the calculations you do take time. So, you know, that's something we should do in future work.
Other questions? I guess I wanted to ask a really Odyssey specific question, which is about the potential for, you've looked at this difference between undrogued and drogued drifters. And one of the challenges for a satellite is thinking about calibration. Does the comparison you've done suggest that drifters will be useful for calibration? Are there concerns that come out of this or reassurances?
Well, I mean, I'm a big fan of them. You know, I mean, we've been comparing these kinds of models to moorings and altimetry, which are also awesome things, but drifters just give you another perspective. You know, what I like about drifters is they give you a global map, and yet you can look at different frequency bands, but it is kind of statistical. So, you know, this study is all statistical. We didn't in this study follow, like, does the model, you know, follow this particular drifter at this particular time. And for CalVal, I suppose you might want something more like that, right?
I think statistics work too, but
Yeah.
people
I
look
mean-
for a variety of approaches, and a satellite like this would certainly need a variety of approaches. I think
mean,
one of the ongoing challenges for Lagrangian measurements is whether the mean actually ends up being the same as an Eulerian mean. Do all Lagrangian particles get bumped into faster water?
Yeah, I mean, you can use the models as a testing ground to
Yeah.
test those kind of things. And I don't know if the S mode people like Tom and others want to. I mean, I think they're using drifters in S mode, if I am correct. But maybe Tom's not on.
We are starting to lose our audience.
Yeah.
Almost the end of the hour. So, any other questions? Otherwise, we should probably wrap up and let people get on with the other things they have to do next.
Yeah, thanks, everyone. And
Thank
thanks
you
to
very
Alex
much.
for preparing the stuff for the inverse cascade calculations.
Brian, I have a quick question, if we're
Yeah.
still on.
Yeah,
The vertical resolution in that upper grid box, I'm guessing it's probably of order a meter, since you're getting things that are similar to those undrugged drifters. Is that right?
it is of order a meter, yeah. And Dimitri made a plot of that for the paper, which I could dig up, but I don't have it with me right now.
Great, thanks.
Yeah, and it's not as good in HICOM. The resolution is higher in the MIT GCM.
That's also, sort of similar to what the expectations are right now, as I understand it, for the Doppler scatterometer instrument.
You mean the resolution of the instrument being about? a meter?
I'm talking about the effective depth range of the measurement.
Oh, okay. Yeah, do you remember, Dimitri? I think your uppermost layer is a meter, right? Yeah. By the way, Roger, you pointed that out in an earlier version of this talk, that we should actually put that in the paper, that, what the actual vertical resolution is. So thanks for doing that. We do have a
I
figure.
thought I had asked that question before.
Yeah, we have a figure in the paper based on that question. Thank you.
Great, thanks.
Well, thanks, Brian, and thanks everyone for engaging.
Yeah, thanks a lot, everyone. I appreciate it.